Hi, welcome back. So we're in chapter 5, prediction by probability. Now it's the time for the lab discussion where we're gonna actually put together most of the information we have accumulated so far on the probability in general inside chapter 5. Now what I would like to do I would like to construct the essential details on lab discussion to follow the previous lab that we have actually accomplished in the previous two books. Research from the start to the end, analysis from the start to the end, and now we are at prediction from the start to the end. Basically, it is the time to start doing some prediction. To rely on the analysis that you have accomplished, to rely on the things that you are assuming to be true. Essentially, I have just put a majority of the framework about probability given the variable could be discrete or continuous. So given the variable to be discrete, we have gone through a number of different kind of distribution. Could be, for example, Bernoulli distribution, binomial, geometric, Pascal, hypergeometric distribution. There are a couple of others, maybe I even added them recently, like the multinomial, for example, or multivariate hypergeometric, which is actually the concept is said the same. Maybe the formula would be a little bit altered. But the important is we understand what does probability mass function mean and cumulative distributive function mean. Of course, we rely also on the expected value and the variance. So that's exactly what I have done here in the left-hand side. Same thing I have done for the continuous by looking at some of the distribution we have actually done before, like the uniform, the exponential, the normal, the gamma, and I've added even the Cauchy distribution. The idea still to some extent remain the same. Let's go ahead now and actually pick up the data set that we have left over from the second book, analysis from the start to the end, and to try to do some prediction on that data set as we have accomplished some analysis and we created our analytical model. So this is the data, and these are the number of variables that are there. Now each one of them have a purpose, and they are not just only randomly selected data sets. So we worked on this data set from the very beginning actually. Next thing maybe we want to check is the shape of this data set. We've got like 91 cases, which is the number of students here, by 12 variables, which we reduced the dimension previously into 12. So we have got the gender, the age of the learner, we've got the pre-trained status of the learner, anxiety score, stress, motivation, aptitude, etc., all the way to the status. The entire project was interested, as we have explored in the research question, that why some learners are dropping out of the course, and this is where the management realized there had been a problem. Now, basically, if we would like to look at describing the numerical variables, such as the age or the other scores. Now, the mean of the age happens to be around 39. The minimum age was 20 and the maximum age was 47. So the mean was 39, which it can give you some sort of anticipation only by numerical reading the age is normally distributed or not. This is the way you can look at the, of course, in numerical reading. Same thing you can do to other variables. I would like to study the distribution of data set just by looking at the graph and then extract some information, and then we start to ask a question. For example, here the gender. We've got male and female. The female happens to be 43 and the male happens to be 37 out of 80. And this is a graphical way of looking at the same exact distribution. So we got the female of 43 and the male of 37. What I'm interested in now is to create a tabulate with a kind of a percentile, and this is I had to do it actually manually. This table is going to be my actual raw material to answer any probability question concerning a discrete kind of variables. Let's go ahead and explore this question. This segment has already enrolled 15 learners to one of the courses. However, in order for the course to start, 20 learners actually must be enrolled. And given the data from the Learn project, in the front of the administrator, there are 5 applications. He's asking a question: what is the probability 2 or more of these applicants are female? That is generalization of a Bernoulli. We know one of them have the probability being female is 54, but we are talking about 2 or more. That means we are interested to find out the probability of X to be larger than or equal to 2. All these guys actually, it represent the exact same answer, looking at the probability of x to be larger than or equal to 2. Now, first of all, what information we know? So to get back to my information here, I know the probability we are interested in is this probability. Now, without memorizing, without looking at the formula, binomial, etc., just think about it from that logical perspective. The idea is I've got 5, applicants, and I would like to choose 2 of them. Let's just start first of all, probably equal to 2. And I know the probability that I'm interested in is this guy here. So I'm gonna multiply this by 5,375. I raise it up to that power, multiply by the minus of this, which is this number here, 4625. Now, this number is gonna give you the probability of x to be equal to 2. But this is not exactly what we're interested in only. We have to sum up 3. So we're gonna do it again when we have 5 and 3, then 5 and 4, then 5, 5. Alternatively, what I could do is a 5 and 1, a 0, and this all you can subtract from 1. So anyway, you could use this one, and this is going to be, I think, 0.855 or something. There is a 53% chance one applicant is going to register be a female. Out of 5, to have 2 or more female applicants, there is an 85% chance that could happen. So as we have proceeded answer for these questions, we were able actually to see 2 important applications for polynomial and binomial distribution. We're going to carry on for the rest of this distribution and see some other question. It's known that after the completion of the course, the head of the project requested actually a random number of final results of the participants. N number of final results were brought at random. The head of the project started looking at the status of each learner. The status, as we have seen in the previous data set, that could be 1 or 0, whereby the 1 have 62.5 status of 1 and 37.5 getting status of 0. All right, these are the probability we know about the status. Okay, so the head of the project started looking at the status of each learner, which could be success or fail, as we can see in here. What we are interested in, how many applicants we expect that the head of the project will go through until he actually can see the first success status. So if you remember, this is a great application of a geometrical way of looking at the problem, or geometrical distribution, because he might open the first and hit it. That's it. It means he accomplished the 62.5%. Or maybe not the first, but it was the second, maybe the third, maybe the fourth, and so on, all the way until the end. It's possible to happen. As we have seen, for an x variable that is distributed with a geometrical distribution with a certain probability that we are interested in, the mu is equal 1 over p. Now, if you get back here and look at the geometrical distribution, we could see that the mu, or the expected number of trials that you can get until you reach to the success that you're interested in, is going to be 1 over p. And the variance is going to be 1 minus p over p squared. So what actually the answer just equal to 1 over, we are interested in the success, so it's going to be 0.625, and that is equal to 1.6, almost 2 applications. So we expect that he can pass the first application and almost the second application, let me say maybe 2, and then the third is going to be most likely to happen to be a successful status. We are asking what is also the standard deviation of that mu distribution. Now we know that the variance of x actually is going to be the 1 minus p, which is this probability here of 0, divided by the p square, and that is gonna be equal to 0.96 or something. And then if you take the square root of that variance of x, right, is gonna be almost 0.97 or something. So this is the standard deviation we expect to derive from this expected value. Now the next question is asking what is the probability of the third application being the first one with a successful result. Well, we want to confirm that. We are interested that the probability of x is going to be equal to 3 actually. This is what we would like to do. Well, that means 1 minus p to the power of 2 multiplied by the probability by p to the power of 1. So another word to say that it's going to be 0.087 or something. Exactly to be the third one, that is a 8.7%. Let's carry on to the next question actually, and the question says the following. The management expect the performance of the project learners to be well. And what is the definition of well? Depends on their code of principle. Says that 70% at least of the learners should pass the final test. So 70% or more pass, we could say that was a good kind of a conducting of a class. That's almost like 16 learners to pass out of 20, because 20 is the standard number of forming a course. Now the head of the project has chosen actually random courses of n learners. So we went through number of courses completely at random. So each course, we know that there are 20 participants. So there were n number of these 20s, and then he selected n number of learners. Total of this was n. All right. Then he checked their status again. So he's interested to figure out what are the status of these n number of students. And now he has number of n. The first question is when the first 0 status will be found in that n number selected. First of all, if we look at this question, we must think of the negative binomial distribution. We call the Pascal a negative binomial distribution. Also, I could think about it as a geometrical distribution, if you will. The first 0 status, which is represent the mu or the average in any way, it's going to be 1 over that probability status, or 375, 2.6 or something. So we are expecting third maybe or more, maybe the fourth, it's going to be our first non-successful result. Now, if we look at the negative or the Pascal distribution, that is m over p. Now, the m in this case happens to be 1, which is, in this case, if you put the m is equal to 1, that is a geometrical distribution. The second one is asking average when will be the third status will be found. And once again, that's going to be 3 over actually the 0.375. Means on the 8th of these n numbers, we expect that the third case had happened of non-success. So 2 happened in the previous 7. The last one is asking what is the probability that the third non-successful case will be found with the 30th application status. We passed the 29. There are 29 before. This is going to be the third. It means 2 had been found before. So if I would like to look only at 2 and 29, that is a binomial distribution. Add 29 chosen 2 with the probability of 0.375 to the power of 2 multiplied by the 0.625 to the power of 27. And now the result of this is going to be multiplied by probability of this case. What is the probability of the last one? The third one is going to be, of course, 0.375. Now, if you do that calculation, you will get, I think, a very small probability of that to happen, almost close to 0. And we are creating an actual probability model to predict something. This is not only applying formulas or reading questions in an exam, but it's a real life problem. And this is how actually we do things in a real setup. Let's look one more question here. The number of learners enrolled in a specific subject happens to be 100. So let's take a subject S, for example. I'd open like few courses, course 1, course 2, a number of courses, right? We have 100 actually enrolled in to participate in this subject. That means, given the fact that we know every course got 20 of them, it means that we got like 5 courses. We figured out that 30 had actually failed with a status of 0. That means 70 of them had got the status of 1. Now, during the inspection time by the management, the head of the project completely at random chosen 50 applications. What is the probability that 15 or more status of 0 will be found? If you remember the hypergeometrical distribution, the idea is fit to be actually applicable in here. We have got 100 applications, right? 50 are chosen. This is the entire sample space, and we're going to 50. In the numerator here, what we have got, what we are interested in fact, we are looking at 15 or more with the status 0 had been found. But we know that there are 30 actually inside the space of 100. So out of these 30, we are interested first to find out whether 15 are found or not. And if we multiply this with the complement of that, the 70 guy, that means there are 35 will be chosen to be successful. We're gonna sum this one. The probability out of this 30, we could have find 16. That means out of the 70, we left to be 34. And again, the sample space still remain the same. Out of the 100, we are choosing actually 50. And you will keep doing all the way down up to out of 30. Actually, we found really 30 of them to have failed, and from the 70 that means left only 20 to complete the sample space of 50. If you calculate this probability, you will get number around 58% or something to find 15 or more zero status in this sample of 50. If you are interested to find exactly 15, that will almost be 17%. Now, let's take one more question. From the 50 random select applications the head of the project has chosen, we are interested in the following. What is the probability that 40 or more will have a successful result? This can fit a Poisson distribution. I mean, the total number of occurrence might occur in a given period of time. Now, out of this 50, measured as a time or a counting space, whatever it is, a volume, then we are expected 40 out of this to have actually this probability. We need to find the lambda. Now, the lambda in this case can be nothing but the MP. And the MP that we have 50 cases multiplied by their probability, which is 0.625, and that is equal to 31.25. So this is my lambda. Probability of X actually to be equal to like 2.5%. Let's take one more question. Now we're talking about the normal learn project classroom. 20 learners must be enrolled. That we know this piece of information in order for the class to begin. Now, a random selected class of 20, we are interested to predict the probability of getting 8 learners with the pre-trained category of 3. And look at the pre-trained 3 categories. We get 1, 2, and 3. Now, we get 20 cases, 8 with category of 3, and then another 8 with category of 2. That is 4 left, should be category of 1. That's exactly what I said. So now to calculate this probability, what we should do, first of all, let's look at the total 20 factorial. And this we're going to be divided by, we're interested in 4 factorial, multiply by 8 factorial, multiply by 8 factorial. Now, this term is going to be multiplied by, well, what's the probability of 1? That is going to be 0.10 to the power of 4. And if you do all of which, going to be 147 or something. So there is like a chance of 1.4% to actually have exactly that kind of a distribution with. That is a multinomial distribution. Perhaps we didn't really go through, but the concept can be derived from the binomial kind of a distribution. Now here in a classroom of 20, now we know there are 20, 7 of them status of 2, 5 happens to be status of 3, 8 with 3 trained of 1. Okay, there's a trainer of the course had randomly selected 10 learners. So he took a random sample of these 20 of 10, right? He chosen 10. And he would like to perform a certain task. Now, question is, what is the probability that out of these 10, 4 with the status of 2, and 4 with status of 3, and finally 2 with status of 1? Now, he is interested exactly in this possible outcome. Now, you might think of the multinomial distribution. Well, that's a legitimate way of thinking. There's no problem. But there is a small difference if you look carefully at this question and the previous one. Now, the sample space changed from 20 to 19 because I kept that one out. This is called without replacement. So in the previous question, the concept of the logic, the 20 kept to 20. That's why we were relying on the multinomial distribution. In this case, we have to be looking at the multivariate hypergeometric distribution. So what the point is that from this 20, I'm going to choose 10. Out of this 8 to choose 2. This is the actual way how we can get to such a probability, which we call it the multivariate hypergeometrical distribution. The next one we'll be looking at case of bivariate concept of probability, and the better is to discuss this from the perspective of conditional probability, given that we are like two discrete kind of variables and we would like to find a probability or to create a probability model to predict a certain value of the joint distribution between these two variables. I did a cross table here to show you the cases of both status and gender. We got the gender of female and male, we get status of 0 and 1. The gender of female happens to have 19 cases of status of 0, 24 status of 1. It seems that the gender of female having a higher percent of status of 1 rather than 0. On the other hand, if we look at the male, we got like 11 and 26. Marginal distribution is read from the edge of cross tabular table. This is the marginal for the status of 0, marginal for the status of 1. If we get back, we will see the same. The same thing we could do with the gender and pre-trained. So these are the counts. Just by counting, you could see female with pre-trained status of 1, they are 6, 23, and 14. So let's go ahead and actually look at the percent as well. Also intuitive, just only by reading about the data. So the first question we are asked about is the following, that the administrator had just received number of application for the upcoming course. Now the project manager wants to know actually what is the probability that the next applicant is going to be female with at least a pre-trained status of 2. Maybe we could consider the X that is going to represent the gender, the Y which is going to represent the pre-trained status. What's the probability that the next applicant is going to be female with at least a pre-trained status of 2? At least means it could be 2 or 3 as well. From the joint distribution, it is easy to see that, well, we are interested in the female with pre-trained 2 or 3. So these are the two probability that we would like to sum up to see the answer of our question. So the probability is actually gonna be the sum of these probability points here and here. Is going to be actually around 46.25%. Now the next question, you got a pre-trained status of 1 is pretty much critical to be enrolled at some course. Now specifically if the gender happened to be male, the manager actually wants to know what is the probability of the next applicant actually being a pre-trained with the status of 1, given that his gender happens to be male. What is the probability? X is going to be equal to 1, given that the Y, which is the gender, is going to be equal to male. That is actually nothing but the probability of X is going to be equal to 1, and probability of Y is equal M divided by the probability Y is equal to M. Well, the probability of having male with pre-trained status of 1, this is the probability of 0.025. Well, the margin probability of having male, it's 0.4625, 5% chance that case might happen. Now, the last question is, during the investigation to establish a specific answer to the research question, actually, I have been asked whether the gender and these pre-trained variables are dependent on one another. First of all, I can check actually the probability of this XY, whether it is equal to the probability of X multiplied by the probability of Y. From different perspective, I could also look at the question like we did in here. Well, if it happens that the probability of X is equal to 1, given that Y is a male, which happens to be this 5% or so, if this probability is equal to the probability of X is equal to 1, probability of X is equal to 1 is 10%. And here we are saying there is a 5% chance. So 5% and 10% are not the same. That's why I can jump to the conclusion they are really dependent on one another. Another way to verify that, if this number here is equal to the probability of female multiplied by the probability of pre-trained 1, is going to be 0.0537, which is different from this number. So we can get to the conclusion that gender and the pre-trained are actually dependent. There is a relationship between them. Maybe we can do the same exact thing by looking at the continuous variables that we have. That's exactly what we're looking at next. I will see you then.